Yeah. So thank you. Well, this talk is going to be about some structures in linguistics mostly. And the main example will be dictionaries that we will think about as graphs. And we will discuss a main notion, that of a loop, and try to see what this loopy feature of dictionaries basically tells us about some linguistic concepts. So this is basically a work with Jean-Pierre Ekman, David Levary, and Elisha Moses. Now, good. So here is the outline of the talk. We will start by describing dictionaries as graphs. We will see their apparent loopiness. We'll give some motivation for thinking about self-reference loops, their emergence in some sort of dynamics of language, and try to suggest a possible link between meaning, concepts, and this simple structure of loops. We'll go on and describe some further details of how loops conglomerate, how they make clusters, and the main core of the dictionary graph. And then we will look into some time-dependent problem, that of the evolution of dictionaries, some history of language evolutions, and see what it can tell us about this structure. Basically, another motivation that I have is to hear from you what you think about possible treatment of this problem. What I will describe is basically a simple observation, just a remark on the structure, and I'm very keen to hear from you, if you have other framework that you think should apply to this problem. So I want to make this talk as much as possible a dialogue. So I want to hear from you some remarks. So graphs are very natural way to describe linguistic structures. We can look at words as vertices in a certain graph, and then think about the evolution of language, in which new words are added to the language to increase the efficiency of communication. They replace, let's say, a phrase or some combination of words. They make it more compact, or sometimes to introduce new concepts, and for other reasons. And then we can look at binary relations between these words, for example, synonyms, or the relation of specific and general. And this defines a graph. These are edges. So for example, in this simple graph, book is a general word, and then specific instances are lexicons and dictionaries, which are synonyms. So we can go on and build a whole graph of a dictionary, of a language, and look for structure. And in the case of dictionary, the binary relation is not a synonym or a general specific, but another type of relation, that of a definition. So vertices are, again, all the defined words, all the list of words that are defined in a dictionary. And we say that edges connect two words if it's a directed graph. So an edge connects V1 to V2 if V2 is part of the definition of V1. So if we look, for example, this is a bit cut here, but never mind, the definition of dictionary, so we see that this is a book which explains or translates, usually in alphabetical order, the words of a language. Then we simplify this this definition, this sentence, into a mapping between the word dictionary and the set of nouns that appear in the definition. So the word dictionary has arrows pointing to book, order, word, and language. Of course, we lost, a lot of the beauty of the language and the content that is in the grammar and in the syntax, etc., etc. But you see that we can still, language is a dynamic thing. So we still can guess the meaning by looking at, if I would give you this set of words, you could have guessed that, they define the dictionary. So some major part of the definition is conserved in the set. So this is the dictionary as a graph. And now we can look at the basic structural properties. And the main example that we used, for reasons that I will explain shortly, is the online dictionary called WordNet, actually the version that is called Extended WordNet. This is an enterprise that belongs to the Princeton University. It's by Kristen Fehlbaum and collaborators. And this is a special dictionary because it resolves the separate meanings of each word. It tells you which of the meanings is used in definitions, in sentences, and then it groups all the words that belong to this meaning into an object called synset. Synset is all the instances of a certain meaning from several words, all the synonyms, and these are actually what will replace the words. This is the vertex of this graph. So if we look at this big online dictionary, we find 80,000 synsets. You can think about them meanwhile as words. And they are connected by about 300,000 directed edges. So this is a rather big graph. And this graph has some very apparent properties. We see that the integrity, meaning how many times a certain word is used in all the definitions of the dictionary, has a very broad distribution. It is a scale-free distribution with an exponent of -2.1, while the out degree, which is basically how many nouns appear in the definition, is very narrow. It's more or less a Poisson distribution with an average of four nouns, which makes sense. A definition cannot be infinitely long. It has a very typical length.
So this is just for nouns. What about verbs or adjectives or things like that?
Well, it's more complicated to discern the meaning, and it's a common tradition in this field to look at nouns. So that's what we do. But in principle, it should be similar also for other parts of speech, like nouns, etc. Like,
Can you say again what out degree is?
oh, so we have this graph. Out degree is how many arrows point out of a word, meaning how many nouns appear in its definition. In degree tells you how many times this word is used in other definition, which can be, there are many common words, and they will have a very large in degree, while the out degree is rather limited.
What is the word which is most used?
I don't know. I should, blush now or something. But I will check after the talk. So it's not an obvious one because we remove all the articles. So what is the, I mean, we can have some guesses. I mean,
guess word.
word?
The word word.
Okay. Another guess? I can tell you after that. Yeah, okay. Good question. I don't know. Fine. So the main observation, the first one at least, is that this dictionary graph contains many loops, much more than you would have expected if I would connect a bunch of 80,000 nodes by edges randomly, by the same number of edges randomly. So it doesn't look like the typical random graph that we know from other systems. Yes?
So you mean with the same condition, that the integer and outer are the same?
Yes. You just, you plot the same number of edges, same number of vertices with the same distribution, connect them randomly, you'll get much less loops. So here is what you see basically. This is what I described as the randomization. This is the number of loops as a function of their length that you would get from a randomized graph. And this is the actual dictionary graph. And you see that in the region of short loops, all the loops that are shorter than 5 words, there is a very significant enrichment of the number of loops with respect to the random graph, which tells you that there is some tendency for loopiness. And we will ask, why.
Do
Yeah.
you have an explanation for that second term?
Some of this is artificial because there are some accumulated errors. If the loops get longer and longer, there is a higher probability that this dictionary cannot really discern between two meanings. I will show some examples. But part of it contains actual loops. But, well, I will show you some examples so we can think about it. Well, this is some, very speculative or imaginative motivation for why we should be interested in loops in general. So, well, we know loops from classical paradoxes, right? Gödel, etc. And there is a major loop in life, that of self-replication, an object that replicates itself. And this is just to tell you that loops are usually somehow linked to emergent objects. Another organism, another object in a class of functions. And dictionaries are inherently cyclic because there are no leaves. Every word should be defined. And this is why we expect loops in the dictionaries, but it turns out that the number of loops is much larger than this constraint. And we would like to see why there are so many loops. So we are looking for possible roles of emergence of loops in evolution of dictionaries. And the suggestions are that loops are not artifacts, they are not some constraints due to the how could I call it? Due to this close property of a dictionary, but something that is natural to the evolution of language. And this is related to a philosophical problem of what is a concept, which I will mention only briefly at the end. So here is a very simple suggestion why loops and concepts should be related. So we can think about evolution of language as a time series in which we introduce words gradually into a language or into a dictionary. So we have the overall dictionary, W, and we divide it into sets of words that are added at each time step. So we have a certain time coordinate in which we embed this graph. And we can look at this definition, this, this replacement of a word by the words that appear in its definition as a certain random walk in this graph. We can start from a word, replace it by all the word in its definitions, replace every word again, and we have this recursive function, if you wish. So we can look at how this process advances in this graph, and there are basically two possibilities. If the graph is a tree-like object, then let's say that we are here, we have WC and WD, and they can replace a word WD that is defined later, and WB can replace a word WA. So if we start from WA, we can go down the graph and replace it by older and older layer of words and get to very old strata of the dictionary. However, if there is a loop in the graph, like this one, I cannot just replace WB by WC and WD, because you see that this word WB is used in the definition of WD. So, this loop should appear or disappear simultaneously, which means that, all these words are interdependent, and this interdependence tells us something about a new concept. All this group of words appear together, and they should have some, common conceptual property, because they are related by definition. So this is basically the suggestion, and we will try to test it in the actual dictionary.
Are you separating out the different? I mean, many nouns have several different meanings, and if
Yes.
a new meaning comes along, you would then add, but you keep the same noun, but you'd add new vertices for this new meaning. How would you?
Yes, this is exactly why we use this version of the extended WordNet, because it separates, it discerns between the meanings of the word. So if I use another meaning, it belongs to another vertex. Okay, so this is what makes this version very, it's essential to us to discern between meanings.
So
Yes.
close as in nearby and close as in shut the door are two separate vertices.
Yes, yes,
They're not.
right. Yeah, otherwise it won't make any sense, right? Yeah. It's important. Yeah, actually, I mean, that was the problem in some previous studies, that, they didn't have this dictionary, so they couldn't discern between the meanings, and, it created a huge number of artificial connections, and, it messed the whole structure. So it's essential. And, well, this is basically what you see if you follow this random walk of definition pathways. So let's say that we have the dictionary. I choose something like 100 words, and I count the number of words that I accumulate along the pathway of the definition. So here is what you see. You see that, they start more or less as, something like a tree-like object, a random tree. They grow exponentially, they expand, while at some point they start to converge to a certain value of about 6,000 words that are all reachable for about 99% of the words. So all these paths contain something like a hair that goes along some tree-like structure, and then it hits a core of about 6,000 words. So basically only something like 20 words along this pathway depend on the starting point, while the rest of the words that are accumulated here belong to this core. They are trapped in this, in this bunch of loops. Well, and you see that this core is somewhat less than 10% of the dictionary. So you can think of the dictionary as this core of clustered loops that is covered by more specific words that go along tree-like structures.
It's the same for different languages?
I don't know, because we have it only for English, but I guess that yes, it shouldn't be so different.
Do you know how strongly connected the core is?
Oh, yes, yes, we will talk about that. Yeah.
Does the core coincide with the most frequently used words in the language?
We will discuss it shortly. Okay. Good. So let's look at these questions. So here are some examples of strongly connected components. So the core is not one strong connected component, but it's connected of a bunch of them. And you see that, they have certain, common concept or meaning in all of them, right? It's quite obvious. And regarding your question, if we look at, the confluence between this core and some known sets of common used words, we'll find a lot of overlap. So here you see the core. So I told you that it's 6,000 words, but to compare it with these dictionaries, I need to go back from these synsets and count words. Not okay. So in units of words, it's about 1,600. Okay. So of this 1,600, you see that in the list of Ogden, this is called Ogden's Basic English. It's something from the end of the 19th century. In Ogden English, there is half of this list. There is 600 nouns in this 850 words. About half of it appears in the core, while if you go to Japan and look at the list of the Japanese education ministries list of essential symbols, this is called the Joyo kanji. If you look at the list of the Joyo kanji, you will find that about 29% of the 1,300 something words also appear in the core. And if you go on and take the most common words in the corpus of the Gutenberg library, you will find even a higher fraction of 40%. And of course, all these lists have also other rather high overlaps. So basically, you see that even across languages, there is a certain core of most common words that tend to be in this core of the dictionary. Some words are missing, but well, at least we have some understanding for why. For some of them, some words are very common, but are yet very specific words like apple, brick, chalk, and they do not belong to loops. They're still very common, but they appear outside the core, and this is why they're missing in the core of the dictionary. And there are other words that we don't understand why exactly. Sometimes it depends on a particular way to define the word. There are alternative definitions, etc., etc. but there is a strong, resemblance of these sets of words.
How far is any, I mean, the typical word who's not in the core from the core? Is it just one step or two steps? Or?
Not too many, I would say. Not more than 10. But 10 is, a high limit. It's a very specific object. But short hairs like 2, 3, 4 are very common. I don't remember exactly, but it cannot be very far. Yes. Yeah.
It could be very far if there's a whole. So suppose you look only at scientific papers, or
Yes.
math and science papers, then there'd be presumably a different core.
Yes, sure.
And that could actually be just another glob over here, right? That's
Yes.
attached to this glob,
Yeah,
as we know when we talk to people.
yeah.
It's like the word momentum
Right.
has different meanings.
Yes. Yes. So, well, if you go and look at very professional dictionaries, I guess that this whole structure will be rather different, because then there is a lot. Yeah, I guess especially in mathematics will be much more tree-like structure, of specific words that is a notion of a more general word, etc., etc. And
I
yeah,
guess what you just wanted to be done. So that would be. Couldn't that be a way where you can then watch the thing evolve, because you can look at newer fields and older fields.
mm-hmm.
When some new thing is invented, then you can study that.
Yeah,
You can look at how the connectivity changes with the age.
yeah. I think it's a good idea. For example, yeah, you can look at scientific papers and yeah, good idea.
But in the scientific literature,
Yes.
a loop would be disconcerting. I mean, if I look up the meaning of a word,
Yes.
like you said, ultimately I keep chasing this thing and I go back to where I started from. I mean, whereas when common language, a loop is fine, because ultimately they're a reference to reality.
Right.
But if it's a pretty formal system, a loop is a nightmare, especially if you know different languages.
Right. I
So
mean,
I expect in technical areas you would have less of that.
right. But
Force, mass, and acceleration. Acceleration is the force of mass.
Language doesn't develop logically,
That's
so
why you're
loops can happen.
right. So you believe that mathematics evolves totally logically?
Does your definition of core have
Yes.
a precise meaning?
Yes. I will define it precisely. Sure. Okay. It's basically all the words that appears in loops, and they are connected to each other, and the core is actually the largest connected component made of these loops. That's what it is.
So if you your D operator that maps
Yes,
a word
yes.
forward to other
Yeah,
words,
yeah.
if you apply D to the core, do you get
Mhm.
core back, or do you get more than core back?
You'd get core.
Do you get exactly D of core equals core? Is it a fixed thing, or
Yes,
or
yes.
core contained in the
Okay,
core?
so you could have subcores which would land in the core after maybe a couple of applications.
Yes,
of D.
yes. So the way to get the core is to cut in an iterative process all the words that are not used in a definition. Okay, so you prune this structure, you cut it until you cannot cut it anymore. Okay, so this defines this fixed point object of exactly what you're looking for.
Wait, can we go back just
Yeah.
a second? I mean, there's okay, so you mentioned as a strongly connected path component, right?
Mm-hmm.
But what you just gave will give you strongly connected path components and paths between strongly connected paths.
Exactly.
So which one is the definition of the core?
No, the definition of the core is not a strongly connected component. It's a bunch of strongly connected components that you'd get from this pruning process. Okay, it's you know.
The
It,
point will be, it's like it's like iterating the D map up to you reach a fixed point.
yes,
Infinite times and you reach a fixed point.
yes,
A fixed set, and
yes.
this fixed set by definition.
Actually, you need to iterate only 7 times.
7 times.
Yes. Yeah. Yeah. There's an infinity, I guess.
So,
Yeah.
as soon as a word is in any loop,
Mhm.
it's in the core.
No.
Because then pruning cannot remove it, right? Because
No, no, no. Okay, okay. Pruning gives you clusters of loops.
yes.
The largest cluster is the core. Okay. Yeah.
So do you notice some kind of partition of the core, so such that you go from, it's easier to go from first partition to the second one, it's harder the other way around?
Sorry, I didn't understand. What is the partition?
Like you separate the core practically was separated into several sets,
Yes.
and it's easier to go from the first set to the second set, but not the other way around.
Mm, mm. I didn't look into this, but I think that there is such a partition. I mean, there are layers inside the core that are more. I mean, it's not a uniform property. It's like, I don't know, some kind of curvature or something. Okay. Good. So this is the definition of the core. You just cut the hairs. You shave it. You shave it about 7 times, and this leaves you only loops. So inside of these loops, there are about 9,000 words. And inside of the largest connected components, there are 6,000 something nodes. And this is the core. And this is some quite useless visualization of the core.
Yeah, why
It's-
is it geometrically like that? Why is it drawn that way?
Just because some algorithm puts springs. I mean, there's no meaning to the coordinate. This is why I said it's useless. But I'm looking for good coordinates. So if you have some, yes.
The fact that you need to shade it 7 times in order to get only loops can be predicted from the beginning.
This is the 7 days in the week.
Well, it tells you that typically, if you define the word, at least in non-professional areas, you don't specify it more than 7 times. Otherwise, you'll get something.
But here's something else. That
Yes.
7
Sounds like
times you
dictionary,
remain
right?
only with loops. It's a different issue.
Yeah.
It's not the number of words in a definition, but
No, it's not the number of words in the definition. But if I go along a hair, then I expect that each step will be going from specific to general, and doing it more than 7 times doesn't make lots of sense. It's
This means that there are only 7 layers of complexity of words.
which I doubt actually.
I don't know what complexity is, but
7 adjectives each word.
yeah, I guess yes. It's like 7 digits, if you wish. Yeah. Good. So well, we have this core, and we want to look at the loop structure in further detail, because we believe that loop means something. So we take this core and we assign to each word or each edge, we can do the same thing, the size of the shortest loop that passes through this edge or this word. It tells us, it tells us something about the connectivity.
So if I have 2 loops,
Yes.
and then a little string running from the top loop down to the bottom loop,
Yes.
that would all be what you're talking about.
Yes. Yes.
That would be one
Yes.
core.
Yes. So here you see one example of a strongly connected component, and with this label of length. Okay, so you see that red is red edges belong to two loops, like the one between point and location. Now, these are words that are used in the definition of each other. There is edge and area, periphery and surface. And other words belong to longer loops. There are many words that belong to a 5 loop. And you see that this whole strongly connected component has some general concept, right, of geography, space, location, something about weather also. There is some relation between the parts of the strongly connected component, which is rather large.
So that is a complete strongly connected.
This is one part of the. I mean, you can get from any word to any other word.
Right, but there's nothing. But in this dictionary, there's nothing more. There are no more loops associated.
Yes.
Okay.
So this idea of assigning loops, the loop label, and looking at a more hierarchical structure that is more common in linguistics gives us alternative structures. So here is an example. This is wheel, and this is how wheel is described in WordNet, which is basically a tree-like structure. It starts from very general objects. Here is entity. It goes to physical entity, object, artifact, the device, etc., until it reaches a wheel downstream the tree. While if I look at the loop structure, I look at all the loops that contain wheel, I see a very different structure. I see, many loops that pass through wheel, and they give me some feeling about concepts that wheel belongs to. So these are sort of alternative bases to describe a word. And here is an example for why many of these long loops are not real loops. So if you follow this loop along the extended WordNet, you see that it starts from a rail car, and you'll get more or less reasonable connections until you get some connection between skill and train, which the automatized automatized loop search gives you this connection, but obviously it's not the train that you started from. So many of these bugs appear because this object is not perfect, and as loops get longer, there is an exponentially growing probability that yes.
Definitions you took from Oxford Dictionary or from where, or you invented it? What
No. There is an online dictionary. It's very important. It's called.
But where does it come from linguistically? Who put it together?
Oh, some guys in Princeton.
So they define every word, what it is.
Yes. They worked very hard
This
to.
was a mistake, for example, train is for training, it's a verb.
Yes. So someone has to. I mean, you cannot automate this definition. Someone has to do it by hand, and at this point, there was a mistake in assigning the part of speech and the meaning to the word train, and yeah. Yes. Put the blame on the university. Yes.
So if this dictionary was recently built,
Mm-hmm.
it could have a different structure than if you use some dictionary that is built progressively over the centuries, right?
Right.
It
Yes.
could have different form, right?
I guess it's not so different.
Historically based. This one is probably not historically.
Yes, but we will discuss history shortly. Yes. Okay. Good. So, just to check that it's not completely artificial, we compared with a previous version of the same WordNet, and the simple Wiktionary that you find in Wiki. And you see that, the distribution of loops is not very different, except for this peak that, you see a larger peak in Wiktionary because we cannot discern the meanings there. But, it's very similar. Yes?
So here when you count this loop length frequency, you actually count for each node the shortest loop going through instead of counting all the possible loops.
Yes, it's a frequency of shortest loops. Okay. Good. So the idea is that loops are linked somehow to concepts, and we would like to see if except from this small scale structure of a loop, we can define a larger scale structure, maybe some basis of loops. So we do something very natural. We try to give each word a coordinate using these loops. So we take all the clusters of loops, strongly connected loops of length that is smaller or equal to 5. Then we find in the core about 400 clusters. And now we take every word, either in the core or outside the core, and we measure the number of paths number of short paths going to each of the clusters. And this gives us a certain coordinate. So we have, to each word, we assign a position, some position in this loop space, which is a vector containing 400 numbers, the strength or this sort of distances from these loop clusters. And now we have these vectors, these 400 coordinate vectors for each of the words. And we have a large matrix that we can then, SVD, we have a singular value decomposition and look for eigenvalues, which are some vectors of loop clusters that go together in many of these words. And if we do that, we see that these vectors are not totally unreasonable. They have a certain, more large-scale conceptual notion. For example, the largest vector is this thing that connects some bodies of water, oceans, America, and some political influence. Interesting. The other one tells you about some relation between cognition, spine, brain. I don't know how old the world enters it. I mean, it's fully automated, but you see something there. This is something about water and plants, I guess. The eighth vector, I'm not sure I'm allowed to talk about. I mean, this is like anyone should have his own explanation for why it comes out, but it comes out, at a very high place. So.
Yeah, sorry, there's 3 and 7 are censored.
They are very similar to other vectors, and this is why they are omitted. But
What's special about the water that is in?
It's an answer to your question from before. What is the most used word? Here it looks like water is.
Okay, so you should remember that here I gave a name to each cluster of loops. So I gave the name water to this cluster of loops. It's not a separate word.
So
Just
old word is a cluster, not a word.
Yeah. A word, yeah. So I don't know. I would like to hear your interpretation of the eighth vector. So, well, you see that you can use this loop to get a large-scale conceptual structure. Yes?
What is the eigenvalues? Are very separate
Yes.
One is very high speed, and then the rest are far away.
It's, I mean, it's not that far, but this guy has
The height.
slightly higher than the rest.
The rest they look almost degenerate, or they are scattered?
Quite degenerate, but I mean, for some time, and then
It's very non-random.
yes, it's well, language is not so random. So, so now, I mean, some of you ask me about history and dynamics, and this is what we do next, because we would like to see how this kind of loop emerge during the history of the evolution of language. So to do that, we need to assign some date to each word, which is more or less the date in which it appeared in the language. So you have some online etymology dictionaries, or you can look in Oxford for the oldest citation of the word, which is a rather good indication for when it appeared. And you can then try to see how many loops appear during a certain period of time. And this is what you see here. This is frequency of loops as a function of the date of the origin of words. And you see two very distinct peaks, one between 1400 and 1500, which is more or less the transition period between Middle English and Modern English. And then you see another separate peak around 1900, which is, if you look what are exactly the loops that appear during this period, you will find that they are mostly connected to technology and scientific terms. Because, you know, this is the Industrial Revolution. There is a lot of scientific literature, etc., etc.
This is one word from each loop? From each of your 400 loops? Is that what you're doing here?
Yes. Yes.
So the fact that, for example, Shakespeare introduced a lot of the new words and a lot of the words in the dictionary around 1600 doesn't show up there because they're not in your...
Well, you know,
They
maybe.
they might be looped to older words. Is that what's going on?
Yes, yes. And anyhow, I wouldn't look at the time resolution of less than 100 years in this dating.
1400 to 1600 is...
Yeah, but you know, it's not that accurate. But it just, you know, the general structure is something like this. I wouldn't go into, you know, more detailed binning of this data.
And also, I guess, although you have between 100, like 1200 and 1500 is the accumulation of like thousands of years, right?
Right,
There's
right.
So many concepts developing
No, I mean, this peak tells you that, you know, all these words either appeared here or, you know, at previous times. It just cannot be dated. Okay. So you see it's not so sharp, but still it's distinct. If you look at if you take a loop and you look for the inter-word distance in years between the times of appearance of these two words inside the loop, you will find that it tends to be less than 100 years, which on this resolution scale is simultaneous. While if you look at the randomized version, you will find that it's much larger. It's around 300 years. So you see that, you know, these loops are not exactly simultaneous, but they tend to appear at a certain period. They're not extended in time. Now you can look at the distribution of these strongly connected components, and it's also something that more or less obeys a scale-free distribution with an exponent of 2.8. And you can build a toy model that sort of explains it. I mean, don't take it too seriously. But if you believe that common words are used more than, tend to be used much more than other words, for example, you say that you connect edges. Let's say that I have a newly introduced word, and I want to define it. I say that there is a higher probability that I will use common words because, I want my definitions to be simple. And if I say that it's proportion to the in degree of the words, the number of times that they are already used in the language, plus a certain constant that tells me what is more or less the attractiveness of a newly introduced word, I can get a scale-free distribution. And then I can say that if loops are added simultaneously and they have a certain probability to connect to an already existing cluster of loops or make their own cluster of loops, I will find this scale-free loop distribution. But I mean, it doesn't really tell me too much because, I can tailor this model to fit the distribution. And I would like really to understand what is the source of this, rich get richer phenomenon, if it exists. So this is basically what we would like to suggest. That words that belong to a loop are related to the emergence of a new concept, and this is the interdependence of words. By the way, how much time do I still have?
Technically 5 minutes.
Okay. So well, this is more or less the suggestion, and this is one nice example of how it really looks like. So here I wrote down the words that belong to the strongly connected component around the word concept. So you see that some of the loops, unfortunately I didn't plot the loops here, but there is an older part of this cluster that appear around the millennium. So part, kind, things, image, nature, quality. And then it builds up to a more abstract word like abstraction, cognition, representation, type. Then concept appears. And then it goes down, I guess, to category theory and perception. And you see that, there is a process of generalization and abstraction of this concept. Well, actually, if you would like to talk about concept, it's a matter of philosophy, epistemology. And there are many philosophers who dealt with this problem. One example is Kant, who suggested that new concepts appear when somehow in the mind there is a set of images that are juxtaposed together, and this juxtaposition gives us a newly emerged concept, and this somewhat corresponds to the idea of loops, which is also a minimal set of words that appear together. I mean, there is a whole literature about these ideas. Just to give you some general context. Yeah, so I guess I need to summarize. So I'll just tell you what are the direction in which we're going, and I would like to hear your suggestions. So, of course, we would like to see whether this exists in other languages. So we're looking at even partially built dictionaries, and we would like to see how dictionaries are mapped to each other. This gives us a higher hierarchy, of course. We did some work on the association network. So association network is what you get if you ask several thousand people what is the a fast association that they get from a word. So we get another big network. And I think, as you would expect, this network is even more loopy.
Is that available somewhere?
Yeah. I mean, if you email me, yeah. So there is a study of something like 6,000 people, and they were asked many times, for a word, and what is the association. Another thing that I didn't have time to discuss is the spectral properties of this graph. This is a big matrix, and you can look at the spectra, and actually you see a very interesting spectra that combines properties of random graphs and more structured objects. It's an interesting thing. Well, you can, apart from loops, you can look at components of higher dimension. Here I got a suggestion from Niels Bass to study simplexes in this big network. We also look at biochemical networks, because this is our vague motivation was coming from the self-replication, the problem of life. And biochemical networks are even more loopy, and most of them are core. Unlike the dictionary that is 90% hair, this thing is, let's say, 90% core. It's almost all loops. And this.
What does the graph look like? What is it?
Oh, so you have, you look at, let's say, the metabolism inside of an organism. So you have, let's say, a list of 1,000 chemical compounds and how they react with each other. And this defines a graph. And you see that this graph is very loopy for good reason, I guess. Well, and here is the summary. We suggest that short loops have some relation to conceptual components of language, of dictionary. Dictionaries have a very typical structures of a strong core made of strongly connected components and long hairs going, not so long hairs, but let's say 7 words going out of this core. We can look at large-scale feature of this core. They gives us some coordinate, and if we add to this loop coordinate time coordinate, the history, the evolution of the language, we can see and suggest that new loops, the emergence of new loops corresponds to emergence of new concepts, whatever concept means. And we can, look at SVD, etc., etc. Basically, the whole idea, the whole approach is that we can use this structure as kind of coordinate that we put on language, on graphs like dictionaries or association networks, and get some, some of the basic structure of the language and its evolution. So I hope that you have some suggestion to how else one can look at these graphs or structures. I would like to hear from you. So, thank you.